on AC power analysis. The content of the chapter is on instantaneous and average power, apparent power, power factor, complex power, and power factor correction. The outcomes. First one is to convert time domain sinusoidal voltage and current to phasor and vice versa, then represent circuits using impedance. Solve steady state AC circuit using phasors and complex impedance. Learn complex power notation. Compute apparent power, real and reactive power for complex load. Draw the power triangle and compute the capacitor size required to perform power factor correction on the load. Okay, firstly, let's take a look on the instantaneous power. What is the meaning of instantaneous power? So as written here, the instantaneous power is written as P as a function of time, T, absorbed. Okay, power absorbed by an element is the product of instantaneous voltage, VT, across the element and the instantaneous current, IT, across it. Okay, so P equals to VI. And of course, it is in watt. It is the rate at which elements absorb the energy. Okay, let's take a look. So let's say we have this system. We have a source here on the left, a sinusoidal source with VT and IT, and a passive linear network on the right side, which is the load. Okay, so VT is written as Vm, the maximum value, cos omega t plus theta V, okay, the phase angle of voltage. Okay, and then the current IT written as Im, the peak value, or M is a maximum value, cos omega t plus theta I, which is the phase angle of the current. So we multiply these two to get the power, V times I. Okay, so this is what we get. V max I max cos omega t plus theta V times omega t plus theta I. So by using the trigonometry identity, cos A cos B equals to 1 over 2 bracket cos A minus B plus cos A plus B. So we convert this term into this conversion. Okay. If you forget about this one, refer to your high school textbook. Okay, so what will happen? Okay, so the A, this is A, this is A. So this is B. So we will get equation of power like this. Okay, 1 over 2 Vm Im cos theta V minus theta I. Okay, this part is due to A minus B. Okay, you can try to prove this one. Okay, and this one is A plus B. Okay, so we get these two parts. Okay, as you can see on the left side, there is no T. Okay, we have T on the right side. Okay, on the second part. Okay, this one. So we have T here. So means that this is depends on time. Okay, time dependent. Time dependent. Okay. So when time change, this component will change. So this is the instantaneous power change with time and is therefore difficult to be measured. Okay, on the left side is the time independent. So it doesn't depend on time. It only depends on the change. The difference of the uh, phase shift. Okay, between voltage and the phase angle of voltage and phase angle of I, the current. Okay, if there is no phase angle, okay, no different, so it is the same, so it becomes 0. Cos of 0 is cos of 0 equals to 1. So we'll only leave only this part. Okay. So if you see this graph down here, okay, the PT graph, okay, is floating. Okay, this is floating. Floating from where? From 0, like this one. Okay, from 0. If there is different in phase shift, if it has no different in phase shift, so voltage and current is in the same phase, it will become like this. Okay, it will go down here. So no shifting, no phase shift. Okay, so what can cause the shifting of phase between current and voltage? Guess what? You can refer to your chapter 5. Okay, chapter 5. Okay, read what kind of components that can cause leading or lagging between the voltage and the current. Okay, if you forget, go to this slide, do these notes again. Okay, so you need to know what kind of component that will cause lagging or leading between voltage and current. Okay, is it this one? Yeah, this one. Yeah, is it the resistor or is it the inductor or the capacitor? Okay, what will cause the lagging? What will cause the leading? So if no lagging or leading, means no phase shift different. Okay, so what components can do that? R, L, or C? You decide. Okay. Okay, next is the average power. The average power, which is also in watt, is the average of instantaneous power over one period. One period is one cycle. One cycle. Okay. So to get the average, we get all the value divided by time of this cycle, this period. So we can integrate the PT equation. Okay. From 0 to t, t is the period. So PV will becomes equals to 1 over 2 V max I max cos theta. The theta here is the difference between these two. Theta V, the theta I. So a resistive load absorbs power all the time. So there will be no phase difference between V and I. Okay, no phase shift. while reactive loop absorbs 0 average power. We can also convert this maximum value into RMS value. Okay, remember how to convert it. Vms equals to, Vms over root 2 equals to VRMS. Okay. Similarly, for IRMS, which is equals to I max over square root 2. So replace it here. Okay, you can get this RMS power. Okay, let's take a look on this example. We have voltage and current equation here. Okay, identify the phase shift, which is for theta V, theta I. Okay. Find the instantaneous power and the average absorbed power. Okay. To get the instantaneous power, P equals to VT. You just fill in the equation. Fill in this equation. Multiply these two. And use the identity. Can get the instantaneous power. Okay, it consists of two components, this one and this one. Okay, let's take a look on this example 2. We have a circuit, a source voltage phasor 5 to the 30-degree angle voltage and 4 ohm resistor and minus J 2 ohm the reactance. So to get the current, where finally we'll use it to calculate the average absorbed power by the resistor. Okay, firstly determine the current V over Z. Okay, Z is the impedance. So the impedance is 4 plus minus J2, so become 4 minus J2, and we get the current 1.118 at the angle of 56.57 degree. So now we have the current. Okay, firstly we determine this one. So the supplied power is 2.5 watt. Now we calculate the average power absorbed by the resistor. Okay. So maximum voltage at the resistor is 4 times I. Okay. So 4 is the resistance of the resistor. I is the current we calculated earlier. So just multiply it and we get the voltage at the resistor, and then use the average power equation to determine the power absorbed by the resistor. Power absorbed by the resistor. Okay. Power absorbed by the resistor. So you see the power absorbed is the same as what is supplied by the source. Okay, due to no phase shift difference. Okay, you can try this example 3 as well. Determine the average power generated by each source and the average power absorbed by each passive element in the circuit. So we have two sources here, current source and voltage source. Okay, you can try to do this. The answer available at the bottom here.